Fantastic. Well, thank you all for joining. It's amazing to see such a full room, and excited. We're all excited to be here to talk to you today. I'm going to give you a little bit of a sort of overview of this space that hopefully will point the direction for some of the talks that are coming later on, set the scene, and inspire you by the opportunities ahead in the space of end-to-end autonomous driving and the applications of that towards embodied AI more generally. So you can't have failed to see the accelerating progress in AI over the last few decades. Breakthrough after breakthrough, covering all sorts of domains, from handwriting, language, speech, computer vision, of course, have been falling year after year at an accelerating pace. And I thoroughly believe that driving is next on this list. But driving is really challenging. You're out there in the real world, surrounded by safety critical scenarios. Here is just one image from the streets of London that we drive every day. This is not an edge case. This is a very normal occurrence. Your system that you build has to be able to deal with that. And the complexity of the real world, the challenges, the variability, and the fact that there are humans, very unpredictable humans, that populate that environment. But if we can unlock the potential here for AI to come out of the cognitive domain, the ChatGPT domain, the generative AI domain, and actually embody that in the real world, the opportunities are immense. And of course, we've all seen these kind of examples from science fiction over the years. But we're really on the cusp of that science fiction becoming reality, a reality for us in our day-to-day lives. And I think, as we'll see in this talk, I hope, driving is probably the first place this is going to really mature into mainstream use for everyday life across the planet. Now, looking back at the last 10, 15 years, maybe, there's been a clear trend from major advances around the sort of ImageNet dataset and AlexNet on top of that, and everything that's come from there in the space of the computer vision community here, of course, leading rapidly on to the amazing advances in NLP with the advent of transformers and the incredible capabilities of next token prediction in terms of language and other forms of generation that we've seen. And really, the next frontier is going to be taking these advances and putting them out in the real world, the open world, the unconstrained, unstructured complexity of that, where safety is paramount. So just to give you another example of the kinds of environments that we are operating in every day, in London, here is again, not an edge case. This is a pretty normal thing, very complex environment with roadworks here. You've got passing traffic. We've got to negotiate out into complex traffic that is, again, very unpredictable, navigate through this. And we're able to do this all without HD maps and just pure end-to-end intelligence. So, what's the difference? What is end-to-end and why is it different? So if we look back to a more traditional autonomous vehicle stack, it looks a little bit like this. So you've got some sensors. Typically, it's a case of throw as many sensors as you can at it because they all, of course, add value in some sense. Pass that into a set of perception algorithms, computer vision algorithms, detecting bounding boxes, lanes, objects, etc. Simultaneously try and localize yourself to a map, often a very high definition map that you've scanned in great detail. And then pass that on to a planning system that sort of predicts what's going to happen next with the other actors in the world, and then a policy that decides how to act given all of that information, and pass that on to a control system that finally actuates it. Now, this can work, right? There are fantastic proof points of this in the world. It does work, but it comes with a very high cost, and nobody has yet done this in a way that is really a sustainable business at scale. And it's very, very challenging to scale for a number of reasons. The perception stack, you have to supervise it, you have to label a lot of data. That's expensive. Furthermore, as a human driver, imagine you could get into a vehicle and put on the world's perfect head-mounted display that turned your camera sensors, your eyes, into a perception. So just visualize the bounding boxes that you get from the perception algorithms and everything else, right? Would you be comfortable to drive from that, not being able to see the real world? I wouldn't. That's a nice thought experiment that I think motivates the fact that you're throwing away stuff, right? You don't know exactly what it is, but you're throwing away stuff. It's an information bottleneck. Next, of course, right, this diagram up the top is quite complex. There's quite a lot of boxes there, and the interplay between them is non-obvious. So even if each individual one you can manage and understand quite well, this is a big complicated system. Those maps, they're also expensive to build. And the more sensors you throw at this problem, the more compute you need, the harder it is to integrate into a vehicle, etc. So instead, what we've been pioneering at Wayve for the last 7-8 years now is really an end-to-end system, and it looks a lot simpler. So similar kind of sensors on the left, although we're very flexible with what sensors we use. Genuinely an end-to-end neural network, pixels in on one side and driving trajectories out of the other side, and then a control system on top of that. And this has, really many advantages in addition to the overcoming the problems that I talked about a moment ago with the traditional stack. It comes with benefits, like it's computationally homogeneous, very easy to deploy to different silicon on the vehicles. We can generalize through data, and we've been doing this the last couple of years as we've been taking what was able to drive just in London on just one vehicle to driving on many vehicles across the UK and now across the US and other places as well. And that all happens through data. It's pretty scalable and an economic solution to this. You can use just cameras if you want to. If you want to throw in other sensors, you can. And we don't need those high definition maps as well. And ultimately it works, and it works better. The performance and safety of this outperforms what we've seen from hand-coded solutions. So here's a few interesting examples of the kind of emergent generalization you get when you put this on the road. So, this top left example, it's learned to pull out of the way, and it could see that vehicle coming. And these are, again, typical narrow streets in London where you've got to negotiate with users. It learns that there's someone coming, there's a gap, let's pull in there, wait for them, and then pull out. Not something we've programmed, something that it learned. Similar example here where it sees that this van is indicating to pull out, and perhaps too politely pulls back and lets it turn around. A slightly more unusual case in the bottom left here with this car that's decided to reverse up the road and find a parking spot. But again, effortlessly handled with ease. And maybe a more mundane example there on the bottom right, but just some clutter on the road. And again, we didn't have to program any of that in. It sort of learns that clutter is to be avoided, so avoid it. We've been working, as I mentioned, on generalizing the driving across different vehicles. We now have it integrated into about 6 different vehicle types. And this little video on the right is the same neural network driving 2 very different vehicle platforms, one following the other as they drive around the streets of London. So I'm going to spend the majority of the time today talking about these 3 topics, which I think are at the frontier of embodied AI research: simulation, multimodality, and foundation models. And again, this will hopefully be a very brief introduction to some of these areas that you'll see more about in the talks that follow the rest of the afternoon. So without further ado, let's dive into simulation. And of course, if you're doing end-to-end driving, well, there's no, obvious way to sort of simulate bits of it. You have to simulate the whole thing. Now that comes with challenges, but it also comes with opportunities. And I'm going to show you some of the latest, work that we've been doing on end-to-end simulation. So here's a few, of the various simulators out there already today. Lots of fantastic work from across the community and across the industry. And they all kind of, in a sense, do different things, right? They all attack the problem slightly differently from different perspectives and with different requirements. And that's perfectly reasonable. What I think is, really important for a simulator are these things on the left here, right? You've got to close the gap. It's not just a visual perception problem, as we've said, it's a behavioral problem. So, you can't just have photorealism, you have to have behavioral realism in your simulator. The world is complex. It's not just a bunch of rigid bounding boxes moving around in a scene graph relative to a static world. The world's more complicated that you have pedestrians, you have cyclists, deformable objects. The lighting is incredibly challenging often. The textures of those objects change, the brake lights, the wipers, the indicators, the traffic lights. It's a really rich world out there. And a lot of the, it's very easy to make seemingly naive, seemingly okay assumptions, but then they really limit you in terms of what you can reconstruct. You've of course got to not just simulate the visual side of things, but the whole interaction, the whole robot interacting with the world. It's got to be scalable, and ultimately scalable really most of the time implies data-driven. And last but not least, you need some control over this. You need to be able to, especially around the long tail, simulate important safety critical scenarios. And I think we're getting there. So we'll talk a little bit about some of the work we've been doing at Wayve that is ticking a lot of these boxes. So we've taken the approach of resimulating the world. So capturing the world from real cameras, as you see in the top left, and then turning that into some form of simulation, resimulation of that scene. And it's been amazing to watch the progress in neural rendering over the last few years that have enabled us to even imagine doing this kind of thing. On top of that sort of reconstruction technology, we've got to turn it into a simulator. And so what we've been building is something called GhostGem, which just turns this into a full closed loop simulator. So you take actions, the driving model takes actions in the simulator that updates the state. You get a new set of images coming back in, and you turn that loop, and you see what happens. Here's a few examples of the kinds of scenes that you can reconstruct there on the right. But what I'm really excited to talk to you about today is something we just launched yesterday, so sort of really hot off the press, which is Prism 1. And again, this really comes back to the critical importance of simulating dynamic and deformable actors in the scene. They're the most vulnerable road users in many respects, and yet so easy to just sort of gloss over because they're hard to simulate. So Prism is a self-supervised 4D non-parametric scene representation that essentially just tries to reconstruct everything it sees over time and give us some control over that. So a couple of examples here in London and the Bay Area. But it's when you get scenes like this with these cyclists and the pedestrians and the complex reflections of the puddles on the water that Prism starts to really come into its own. It's able to actually reconstruct those pedestrians as they're pedaling, and it's not just some kind of rigid cartoonish cyclist or pedestrian that you're seeing here. Oops. Here's another example where we're deliberately now perturbing the camera path with this sinusoid to show we've got that level of control here. This is a simulator, and I mean some really remarkable things here. I think first of all the fact that we're getting this pedestrian at all with their umbrella, and then all of the complex lighting and reflections off the water on the road there. Furthermore, the traffic light you see up there changes color as part of this simulation. Here's another example where we're doing some more new view synthesis. It pauses here and pans to the left and right. And again, it's really important to be able to do this, because if you've got a closed loop simulator, it's going to drift off the path that you drove originally. And so it's important to be able to see what, to let that simulator play out. In these examples, instead of letting the car keep driving, we've sort of frozen the camera, and we're moving time backwards and forwards. So you can see that the dynamic objects in the scene are they're moving. We're able to reconstruct those in beautiful accuracy. And furthermore, again, things like the traffic lights, which would be hard to approach in other ways. And a couple more examples here with challenging lighting conditions, reflections on the road, the glint in the building up there. Subtle things but they do matter when it comes to testing the driving models that you're building to a level of fidelity that you need. Now, as part of developing Prism, we have also been, of course, using an internal data set to benchmark this and to track progress. And we're delighted to also share this data set. It's called Wayve Scenes 101. You can download it from our website. And this is designed specifically to help the community to focus on this problem of 4D scene reconstruction. It's super important. I'm sure there are, you all have amazing ideas in the audience here of how to improve this even further. And we hope to sort of empower and excite you to do that. It's got, a variety of scenes, different countries, different road types, weather layouts, weather lighting conditions, lots of cyclists and pedestrians. And we've even specified a held out camera so we can test new view synthesis in this particular, a nice way. Hit just 3 examples, relatively simple ones in these cases, but showing the variety of different lighting conditions we've got here, from sunny to rainy to dark. But perhaps more interestingly, we've got some really, really challenging scenes in here. So this top one harks back to the first slide in the talk with all these pedestrians crossing the road. And again, a true simulator for solving autonomous driving is going to have to deal with these kind of situations. But of course, you want to go beyond just resimulating exactly what happened, and to be able to create new things as well. Here, both we can combine the neural rendering and generative AI to start to bring this up and simulate these rarer edge cases. So this time last year, we launched Gaia, which is a generative AI for autonomy, a generative world model. And essentially what that means is you can predict you can generate videos, but you can controllably generate videos. So you can action condition it on what can come next, or indeed language condition it to tell it, what the weather should be like, or what objects should be present. And this is architecturally a fairly straightforward next token prediction plus some video diffusion on the end. But as you'll see, as you'll see in a second, came with some really amazing results. Of course, this has become a really exciting and crowded field over the last couple of years now, and delighted to see further progress in this space in the years to come. But here's a few examples of Gaia just being left to its own devices. Just let it generate. Don't try and control it or anything. And I think the beautiful thing about this is these are long form videos. It's generating these for long periods at a time. It's generating a variety of different road layouts, conditions. It's able to deal with the dynamic agents. It's got some clear sort of mental representation of dynamic agents versus the static scene. And they're certainly not perfect, and there's rough edges around them, but on the whole, it looks pretty convincing. you can do some nice things with this. And one of my favorite is producing diverse futures. So you give it the same starting point, and then you let it, diverge. And so in this example, on the left, the white car in its imagination has reversed and let us pass, but the white car on the right has decided to pull forward, and we then give way as the ego vehicle. We can also control it though, and this is where it starts to get back to simulation. How do we, start to close the loop here? And in this example, we deliberately steer the ego vehicle towards the oncoming traffic, and lo and behold, Gaia imagines that this oncoming traffic swerves out of the way to avoid us. More recently, we've been looking at how to use Gaia to add objects and join the dots between what we saw with Ghost Gym and Prism and what we've just seen with Gaia. And in particular, one thing that's looking really exciting and promising is the idea of just adding objects realistically. So here we're taking a reconstructed scene from Prism and drawing this cuboid of where we want a vehicle to be, and then letting Gaia fill it in. And lo and behold, a car appears with realistic lighting, realistic shadows, etc. A couple more examples of a bus and 2 more cars here. And then here's a video example where all of the dynamic agents here now are being in-painted by Gaia as it goes. And there's some really interesting, remarkable stuff, especially around the fact that there's, this is multi-view generation, and we're able to, accurately infill this object in both cameras simultaneously. And then, back to Prism, I think, another really interesting topic here is counterfactual simulation. So taking something that really happened and then changing it in some way. So here we're taking this pedestrian, removing that pedestrian, and then, you can compare A versus B, what your driving model does in these situations. And this is a really, really clean, clear, and I think causal demonstration, therefore, of what matters to that driving model. So I expect to see much more around counterfactual simulation in the months to come. Okay, moving on, then the next topic I wanted to touch on briefly is multimodality. And really, this is all about language, and language meets driving, which sounded completely crazy when we started this a couple of years ago, but I think hopefully probably does not sound quite so crazy anymore. Opening up all sorts of applications from explainability to the, improving the raw intelligence of the driving, and building trust and safety around autonomous driving. And there are so many exciting applications here, but the first one I want to talk about is Lingo 1, which was a grounded visual question answering model that we put out a few months ago. And here, relatively simple architecture again, put in a snippet of your video into some encoders, into a large language model that's been fine-tuned, and then turn that into a dialogue loop. And we sort of explored this in two modes, one just generating commentary, as you see on the left. So here we're driving along, it's saying I'm maintaining my speed. I'm slowing down due to a jaywalker. I'm slowing down in preparation for the upcoming left turn. And on the right, you've got a true VQA system where you can ask what it's seeing, and it will describe that, and you can keep, you can keep refining and asking more questions as to what's going on in the scene. We extended that with Lingo Show and Tell, which now you can ask it things like, what are you paying attention to? And not only will it tell you, but it will also, draw with sort of a semantic segmentation type output overlaying onto the video to really sort of connect what it's seeing with what it's saying. But more recently, we've started to extend Lingo and released Lingo 2, which is all about not just commentary and explainability, but actually driving at the same time. So I believe this was the first language and driving model that went out on public roads, actually controlling the vehicle as well as being able to explain its actions. And so a few examples here: accelerating, increasing speed, making a right turn to stay on the route, reducing my speed for the upcoming turn, turning right to follow the route, etc. And this is the same model that is producing the text is also actually the policy and producing the driving commands here. Keeping left to follow the route, turning left to follow the route. Another example: reducing speed for a turn, turning right to stay on the planned route, increasing speed limit to meet the speed limit, reducing speed due to jaywalkers, moving past a parked vehicle, keeping speed, the road ahead is clear, the zebra crossing is clear, keeping speed, the road is clear. We can also now join the dots between the language models that are driving that we just saw with Lingo 2 and the simulation technology, and use simulation to explore controlling the driving system with language. And so in this example, we've got a simulated environment where we ask it to stop behind the bus on the left and instead to overtake the bus on the right. And lo and behold, this language-based prompting changes what happens with the driving, as you'd expect. And I think the next thing here is back to those counterfactuals, changing things. So here we're taking an original video and using Gaia to insert these vehicles. So that's the only thing we change. And then we look at both, how does the driving plan change? And that's these sort of wiggly lines that are probably a bit hard to see on the slide, but also how the text change. And so on the top left, it says increasing speed to match the speed limit. On the bottom left, it says slowing down to match the lead vehicle's speed. And on the right, stopping due to the red light and stopping behind the stationary traffic. So again, it's this: you change one thing in the scene and you explore what happens. And if you can do that successfully over a statistical sample, you're getting some really good confidence about what's going on in the brain of these models. The final thing I wanted to touch on today is around foundation models for embodied AI. Now, a foundation model, as we've all heard the term bandied about, but I think this is a pretty decent definition. It's a model that's trained on a diverse set of data that can be adapted to a wide range of downstream tasks. And of course, huge progress in the community on this the last few years, certainly starting with language and then language and vision coming together. Major advances on this slide, of course. More recently, in the space of embodied AI, this has also been garnering attention. And sort of my favorites are these ones at the bottom, and especially the ones where you're starting to see cross-embodiment results, where you can train across multiple different robotic embodiments jointly and get better policies for each of those embodiments than had you trained specifically for that embodiment on its own. I think that's an amazing result. And I think really points to the future here, where we can start to learn from from vehicles and from humanoid robots and any other kind of robotic embodiment, and take the data and learnings from all of those and combine those together into something that's bigger than the individual parts of this. Now, when it comes to foundation models in embodied AI, there are some genuine hard challenges that are distinct from the more traditional cognitive AI foundation models we've seen so far. Data being perhaps the primary one here. The data just doesn't exist on the web, right? It's not like you can go and scrape crawl the web's web pages for text, or crawl YouTube or equivalent for videos. It's not there. So you have to find it somewhere. Now, turns out in autonomous driving, that's relatively straightforward compared to some other forms of environment. You've got all of these cars now, almost all modern cars are equipped with loads of cameras. There's dash cameras out there, etc. So I think autonomous driving is where you can actually solve this. But it is going to be challenging nonetheless. Once you've got all that data, of course, that's a lot of data and you've got to process it. And that leads to huge compute demands for training. And finally, you've got to deploy this on a robot of some description. And robots, as you may know, if you've worked with them, don't always do what you ask them to do. You've got the challenge of distilling a big foundation model down onto something that can run at low latency on an embedded chip. You've got that highly ambiguous, uncontrolled operating environment you've got to work in. And of course, you've got to deal with the safety and validation of this. But as I say, in the space of driving, I think we can make some real progress here. You can get internet scale video data. You can get a subset of that that's slightly smaller, which is more around embodied video. You can get large scale driving data from deployments of existing vehicles around the world. And then you don't need much on top of that. The icing on the cake is high quality driving data that you actually learn a policy from. And, I think it's really interesting to look at, this kind of diverse sources of data and question, is it useful? Is this useful? And I think the answer is yes. I think, each of these videos has something interesting to tell us about the world, how the world works, how humans work, how physics works. And so I do think that there's a lot of value to be had by learning from a very diverse set of video data and other forms of data to help us, even if all we care about at the end of the day is the driving task. And so ultimately, I think these multimodal foundation models are going to help us unlock safe and generalizable autonomous driving, and hopefully much more beyond. So to wrap up today, thank you for joining us for this tutorial. I do think embodied AI is the next frontier in AI, and that self-driving is the way to get there first, to show the value to the world of embodied AI. We've seen how advances like Prism and Gaia are helping us to simulate complex dynamic scenes end to end. We've seen how language can help us with explainability and building trust and understanding of how these end-to-end systems work, and how embodied AI foundation models are going to be one of the key levers to extend this further. So with that, I will wrap up. Thank you again for coming. You'll see us around. There's a lot of us from Wayve here this week. We've got a booth on the floor. We've got the rest of the tutorial this afternoon, of course. And please come talk to me, talk to one of the team. I would love to engage and continue this conversation. Thank you.
Thank you, Jamie. Thank you, Jamie. So we have a few minutes for questions. So, yeah, you want to?
So you did explain about Gaia and how you can create scenarios, right? How do you go from, say, creating new scenarios where you can plug in stuff to creating the actual tail scenarios that we care about? For example, something falling off the back of a truck or something. Is that coming from user prompts that we write today, or is that also automated, or how do we think of that?
Yeah, so I think, so the question is, how do you go beyond just sort of inserting vehicles to generating more complex scenarios? And I think that's one of the big challenges in simulation, right? It's not just doing it. I mean, I think that could be done by hand relatively straightforwardly. But the question is, how do you do it scalably? How do you do that? I'm not going to claim that I have all the answers to that today, but I do think that's really the crux of this challenge is how do you keep pushing the envelope there in a sustainable, scalable way?
You can generate rich and realistic data recommendations. Why don't we use that data instead of using foundation models?
Yeah, so the question is, we can generate synthetic data. Why do we use those rather than foundation models? I'm not sure the answer is that you don't, it's one or the other. I think you can certainly think about both. And I think when you think about, I think it's especially around safety critical scenarios, they're not going to be things that you're going to be able to capture much of yourself. Now, there may be dash cam footage and in quite some volume on the web that does capture those kind of safety critical scenarios. But even then, I think there are very good reasons why you might want to simulate those more programmatically. I think you also very quickly get into the sort of interesting, almost philosophical debate about, is it better for a model to learn from the entire web versus, rather, what happens when the web is entirely simulated, it's synthetic itself, right? When ChatGPT is spat out almost every website on there, can you still learn from that? Can you still get value from that? I think there are some arguments both directions, but yeah.
Thanks, great talk. I had a question about, do you think like Gaia and Prism are kind of becoming a virtuous cycle in that way, that first you get a real world scenario and then you use Prism to simulate millions of those scenarios and then go back to Gaia? So it feels to me that they're like kind of becoming one thing.
Yeah, I think there's definitely some convergence between Gaia and Prism. I think exactly where that takes us, we will see. But yeah, you could certainly imagine taking a fully generated Gaia scene and then resimulating that and that giving you more levels of control. I said, yeah.
Someone found it back.
So you really showed some great capabilities from Prism, Lingo, Gaia. I'm interested, where in your production pipeline of development, testing, validation, deployment, vehicle testing, evaluation, where do those tools play a prominent tip and where do they play a prominent role in data?
Okay. The question is basically, where do all of these things that I talked about today show up in our production stack? I'm not going to talk about our production stack, so I'll say that up front. But the mission of the reason we have a science team at Wayve, that we can invest in these kind of fundamental research breakthroughs, is precisely because we want to take that into production, and we want that to impact our stack, and we want that to accelerate the progress that the company is making. So I won't answer with any specifics for obvious reasons, but absolutely we are pushing these as fast as we can into production.
Is there any systematic way to evaluate the generated work that it resembles practically?
Yeah. Can you evaluate the realism of the generated world? I think that's a really interesting question. I don't know, maybe Jennifer will talk about it a little bit later on, but I think there's a more general version of that, is how do you evaluate the realism of a simulator? And I think that there are lots of approaches, all of them imperfect, that are the ones I've come across so far, but all add a little bit of value. So you can look at the realism of the generated scenes. You can look at how faithfully it's able to recreate an existing scene. If it's a fully generated one, though, it becomes a bit more challenging. But then you could start to look at distributions of behavior in that simulator, things like that.
Question from a safety perspective. How would you anticipate or wish to see safety research change to be able to support this kind of endpoint? What would you say to the naysayers effectively and convince their perception of what it takes to do this?
Yeah, I think so. What would I say to the naysayers? Well, I think part of it would come back to that thought experiment I did earlier, which is would you put on an HMD and drive your car around the real world only seeing bounding boxes? I think that's part of it. I think part of it is that you can get the feeling of security from testing each individual box in that complex thing, but when it comes to the whole, you still have to test the whole as a system, and that's no different to what we have here. I think, and then I think the other thing is just the mounting evidence that actually it does work better in practice, and so because of that, I think you just have to that doesn't mean we've solved all the problems around safety by any means, but we need to go and invest in that, and we need the community here to engage in that process and to be, you know, to be part of that, and to, you know, put that sort of skepticism of end-to-end aside and think, okay, this is happening, it's real, it's working. How do we now go and build that safety assurance that we need?
Last question.
But they're asking from outside.
It's not broadcasted, so but we will have recording released later. We'll have recording released later.
But it's not kind of doing this.
That's for the present post. Right, so is this, let's thank again, Jimmy.
Thank you.